Okay, the fundamental theorem of calculus. Now, I'm sure that many of you study calculus now have already used the definite integral, or at least know how to use the definite integral. Okay, but I believe that somehow maybe we've reached a stage, or at least for me, or maybe in the crop of high schools in America or in Singapore, we've reached a stage where we really do not know the meaning of what the definite integral is, let alone how it was proved or where it came from. Now, not to say that whatever we are doing now is wrong, but to say that I believe we should really take an attempt to look at the work or the marvelous work of the mathematicians before us to find out how they came up with the definite integral. Okay, and that occurs when they showed the fundamental theorem of calculus, which is what I'm going to try to reenact, or which what I'm going to try to prove now. Now, I must say that it's not an easy task, so if I make any mistakes, I hope you forgive me, but I try my best to see, I try to the best of I can to prove it. Okay, and it starts now. Okay, so the definite integral of function x from a to b is this thing over here, which if the proper term, or what you would sometimes call it, is the Riemann sums. Okay, so if I were to draw a graph here like this, okay, and let's just say from a to b, okay, this will give me, as you all know, the area under the graph. Okay, and by the first method, or the first way that came out first, was to sum up the individual areas and let the change in x equals to 0, Riemann sums. Not a problem. And this is not a problem when we're dealing with simple functions like x and x squared. However, it came to a point where they asked themselves, my goodness, what about if we have to evaluate a complicated function such as x squared times root x minus 4 divided by x minus 1? That's going to be quite difficult, okay? And that is why they needed another way to really, or a much easier way to evaluate this one over here and not take the functions or the sum of the functions of each of the small bits, okay? So when they look about it, it seems paradoxical at first sight, but they ask themselves a different question, okay? Instead of finding the area from a to b, why not we find the area from a to a variable point x over here, okay? Now, I do not know why they did that. Well, I must say now in retrospect, because we can maybe manipulate the algebra, but that is what they started out with. So let us try to find the area from a to a certain point x over here to see what we get, to see whether we can make this something easier to find out, okay? And it started out like this, okay? It's first we must establish the fact that dA, where a is a function of the area under the graph, and I emphasize again the area under the graph is equals to function x, where function x is the function of the graph. Now, this may seem a bit obvious to you, it may not seem obvious to you, but we still need to show that, which is the change in the area is equals to the function x. The rate of change of the area, okay, with respect to x is equals to the function x, okay? Now, when I look at it, it doesn't seem that obvious, so we will try to show that, okay? And what we're going to do is that we're going to differentiate this using first principles, which is, I write it out, the limit as change in x tends towards 0, and writing out fully is the function area, function a, x plus change in x minus ax divided by change in x, okay? We're just simply employing differentiating by first principles, okay? That's easy. But now we need to somehow have an interpretation of this thing over here, okay? And for that we need to draw a graph to really see what's going on. Okay, so I got a graph here, okay, and I got x here and x plus change in x over here. Just like always, okay? Function x here. But bearing in mind, and I say bearing in mind again, that a is the function of the area under the graph. So let's just take a look at this. The area from under the graph at x plus change in x, which is the area here, okay, minus the area under the graph at point x, which is the area here. So the top one over here gives us the area over here, okay? Just take a look at it and you would see that I'm correct, okay? Now, there's another way to represent that area, okay? And that is to take the base, which is the change in x, the base, times by a midpoint over here, okay, x dash, times by the height, which would be function f x dash, okay? The function f, and you put in the value of x dash inside, where x dash is the midpoint of here and here. Now, to get this, you need another theorem called the mean value theorem, which I will probably show in another day, but for the sake of calculus, we will just take that as really proven it. Okay, but basically it's telling you that we can take the midpoint and the area balances out, the deficiencies of the area balances out if the base is small enough. Okay, so now that we got this over here, we can represent the area, okay, by taking the change in x times multiplying that with function f x dash, okay, which is equals to limit change in x as change in x tends towards 0 of function x dash times by change in x for the area over here, just like how I've showed you that we want to find the area over here divided by x dash, cancel out, taking the limit. Now, as change in x tends towards 0, you will see that this point tends towards closer to this point over here. That will also mean that the function here, or the point here, will tend closer to the point over here, okay? Which down here is function x, not x dash anymore. So, we can just simply write that out as function x. Yeah, function x, correct. And we have established the one over here, okay? Using differentiating by first principles.